Swayam Prabha. Digital India. Educated India.
Hello everyone. Now we will discuss one important aspect of roller drafting, that is roller setting, and theoretically we will try to understand its impact of this roller setting on the fiber, that is sliver unevenness. Okay. So, what is roller setting? Roller setting is the distance between, this is the front roller, back roller. So, distance between the nip point, that is roller setting, and this roller setting depends on the fiber length. So, as the fiber length increases, we have to have higher roller setting, and ideal case we have discussed that the roller setting is equal to the fiber length, when fiber lengths are all the fibers are of equal length, but in actual practice the roller setting will be different. It will be little bit more than the fiber mean fiber or sorry effective length of the fiber in case of cotton. Now, let us try to discuss the impact. So, it is evident that the minimum irregularity was obtained at the setting less than the maximum fiber length. So, when we are talking about the fiber of different length, so as we reduce the fiber setting, so irregularity will be reduced. So, the maximum fiber length whatever, so we will set the fiber the roller setting, if it is less than that, then irregularity will be reduced. But the main problem will be there, in that case the spewing effect will be there, as we have discussed earlier. Now, here if you see here, so x axis is the roller setting with relative to the fiber length parameter. So, let us see it is a maximum fiber length. So, roller setting is divided by fiber length, maximum fiber length. So, if roller setting is equal to fiber length L, maximum fiber length, so when in that case it is 1, the ratio is 1. So, at that position it is actually with respect to effective length. If it is with effective length, here with respect to maximum fiber length. So, here S is the L is the effective length. So, if S equal to effective length, in that case the roller setting will be lower, but if it is more than little bit more than effective length, then we will get the minimum irregularity. So, this is the irregularity. So, that is why based on effective length if we do, we set the roller setting. So, L effective length plus little bit more than that. So, that will result the minimum irregularity. As we go on increasing the roller setting, then the floating fiber will be there. So, more and more floating fiber will be there, then it will result the irregularity. But what will happen if the roller setting is less than the effective length? So, if it is less than the effective length, that will due to the spewing effect, that clustering clumping of the fibers will be there at the front roller, and that will increase the irregularity, and for if on the basis of the maximum length, it is actually at the around say 0.885 or 86, 0.86, it is maximum, that minimum irregularity is we observe the minimum irregularity. So, a greater setting, a rapid increase in irregularity occurs. So, a rapid increase in irregularity occurs because longer fibers as well as the short fibers become floating. So, here the longer fibers say effective length, beyond that this longer fibers become floating. So, that all the fibers will be floating. The distance over which the short fibers float increases, both factors give more pronounced drafting wave. So, this will result drafting wave. The reason why spewing does not present a problem at the setting minimum irregularity is the number of maximum length of fibers, usually less than 5%. So, only few fibers would be nipped by both the roller. So, if we set the fiber based on the effective length, in that case very few fiber, typically less than 5% of the fibers will be gripped by both the rollers, and spewing effect does not occur. Spewing effect only occurs if the large quantity of fiber, large number of fibers are under the grip of both the rollers. However, to ensure against spewing effect, a setting slightly wider than the corresponding minimum CV is required. So, here it is a minimum CV, we try to set the fiber the roller setting little bit more. So, here minimum CV is there, minimum CV is at the say effective length, it is equal to effective length. So, we try to set beyond the minimum CV, okay, so that to avoid the spewing effect. Spewing effect will be actually, if it is there, then it will generate the additional unevenness. Now, we will discuss the Vesilef's model of drafting and irregularity generation. So, theoretically model is there. So, let us see. Now, in Vesilef model, so there are fibers in the back, some fibers at the back roller nib, and this is the front roller nib. So, back roller moves at the speed V0 and the front roller moves at the speed V1. What does it say? So, fibers are divided into two groups, one is short fiber, another is long fiber. Intermediate fibers are not considered here. So, long fiber is suppose it is considered short fiber is by A and long fiber is represented by B. So, two groups of fibers are there. To start with, let us consider the movement of two fibers only. So, we will discuss only the movement of two fibers. The fibers belonging to short fibers and long fiber groups are represented by A and B. Let the short fiber, which is actually be ahead of the long fiber. So, short fiber is ahead of the long fiber, the leading end is ahead of the long fiber by y bar. So, by y bar the leading end of the short fiber A is ahead of the leading edge of the long fiber, and vertical line indicates the front and back roller nips. So, these are the front and back roller nips. Let y bar, the distance between the leading ends between short fiber and long fiber, that is shear before drafting. So, this distance here y bar is the, that is a shear, that is fiber leading end distance, that is shear before drafting. L is the length of the long fiber, LT is the length of the long fiber, which is equal to the ratch R. Ratch means the nip to nip distance, the setting. In this ideal condition, we assume that the roller setting is equal to the long fiber length. Okay. Ratch R. So, L equal to R, D is the draft, that is the D is nothing but V1 by V0. So, that is the ratio of the speeds. A is the floating length of the short fiber. So, here is the, at the point case 2, we will see the fiber, the short fiber is about to leave the back roller nip, and it needs the distance A to reach, it has to travel distance A as a floating fiber to reach the nip of the front roller, that is line A. So, A means floating length of the short fiber A, and long fiber there is no floating length because it is equal to the ratch, fiber length is equal to ratch. U is the average floating velocity. So, you have 3 velocities coming. So, initially the fibers moving at the speed of the back roller, which is under the control of the back roller, moves at the speed V0, and fibers under the grip of the front roller moves at the V1, but U is the average floating velocity U. So, that means V1 will be more than U, U will be more than V0. So, that is the, this is the average floating velocity within this zone, and V0 is the velocity of the back roller, feed roller, and V1 is the velocity of the front roller. So, with this condition, and y dash bar shear after drafting. Now, y bar is the shear before drafting, y dash bar will be shear after drafting. So, what will be there here? It will be drafting of the, that movement is there. So, drafting of the short fiber is moving. So, short fiber is moving. So, y bar will be definitely equal to y1 bar will be d multiplied by y bar, because it has moved at that speed. So, in stage 1, both fibers A and B are partially with the drafting zone. Okay. This A and B, they are partially within the drafting zone and moving at the same speed, at because as they are under the control of the back roller, they will move at the speed of the back roller, that is V 0. In stage 2, this is in stage 1, in stage 2 the short fiber A has actually is leaving the back roller nib. The short fiber A is about to released from the back roller nib and has to cover the floating distance A at the speed u to reach the delivery roller nib. But the long fiber will continue moving at the speed of the back roller nib. So, that is the situation. Now, time taken for the short fiber to reach the delivery roller nib. So, its speed is u and A is the distance. So, time will be taken will be the, this is the say meter per second. So, A by u will be the time taken by the short fiber to reach to the nib. So, from the second stage case 2 to case 3, it will take A by u time. So, A by u is the time. So, by that time the short fiber reached the nib point of the trailing leading end of the short fiber reached the front roller nib and it is about to start at the speed move at the speed of the front roller, where u is the floating velocity. Now, the time t1 taken for the long fiber. So, t was the time we have discussed, this is the t is the time taken by the short fiber to reach the front roller nib. Now, the time t1 taken for the long fiber b to reach to the delivery roller nib from the time where the short fiber has started floating. So, from this point at this from 2. So, when at this point from 2 to 4 that time, that is the time where the long fiber will travel by a plus y bar to reach up to the front roller nib, and here initially it will start. So, it will move at the speed of v 0. So, that is the time t1. So, y bar plus a is the distance travelled at the speed of v 0 at the bottom. So, that is the time taken. Now, let t2. So, t1 is the, let t2 be the time taken for the short fiber A to change position from the stage 3 to stage 4. Stage 3 to stage 4, during this time fiber A moves at the speed v 1. So, that here stage 3 to stage 4 fiber A moves at the speed v 1, that is the t1 minus t. So, the t2 will be t1 minus t, that means t1 is this and t is a by u. So, that will be it is a minus t, because in between this is the 3 comes in between the second and 4. So, that is why T 1 minus T will be there, it is subtracted. So, we will get the equation. So, T 2 in time T 2 fiber A moves at distance y 1 bar. So, y 1 bar is the distance it is moved. Now, try to see. So, y 1, what is y 1 bar? It is V 1 multiplied by T 2. V 1 is the fiber that front roller speed. So, V 1 into multiplied by T 2, and T 2 we know, this we have derived. So, V 1 multiplied by this T 2 is there. Now, here if we see, so T 2 from the last slide we have got. Now, if we multiply, so V 1 by V 0 y bar. So, y bar is the distance initial shear, initial distance between the tip of the short fiber and long fiber, A multiplied by V 1 by V 0 and minus A multiplied by V 1 by u. Now, what is V 1 by V 0? It is nothing but draft, the ratio of the speeds. So, this is d y bar A into d and A V 1 by u. U is the floating velocity of average floating velocity. Now, this term alpha we can get, where is alpha is we can replace with this term. So, this is okay. So, A is that alpha equal to A d minus V 1 by u. This term can be termed as alpha. So, this is alpha. So, dy bar plus alpha. So, alpha is the term which is actually is function of draft, this main velocity A. So, all these terms are there. So, alpha is known as deviation from the normal shear. So, for normal shear it has to be d multiplied by y bar. So, the thing is that for ideal movement of fiber, the y bar should have been y 1 bar should have been y bar multiplied by d for ideal movement. But due to the floating fiber move at the speed of u. So, the ideal it is variation. So, alpha is the deviation from the ideal case. So, the deviation is shown by alpha. So, this is the deviation here. So, this deviation is a function of the draft, mainly the floating fiber movement and how much it is travelling. So, more distance travelled by the short fiber, that it will be deviation will be more. Ideally, the distance between the leading ends, that is normal shear, would have been d y dash, that is ideal case. However, due to the floating velocity u of the short fiber and also due to the floating distance, has to be dy bar plus x. So, more the floating distance. So, that means what does it mean? If we have fiber length shorter, the short fiber higher the short fiber, higher will be the deviation. Okay. So, that is there, and the floating velocity. So, that is the deviation alpha, and when the floating velocity u equal to v 0. So, this when the fibers move at the speed of back roller, floating fibers move at the speed of back roller, that is alpha u equal to, this is a v 0, that is this is v 0. Now, we can see alpha equal to a multiplied d minus v 1 by v 0. So, this is nothing but draft. So, a d minus d, so it will be 0. So, alpha minimum is possible, minimum alpha is there when the floating fiber moves at the speed of the back roller, and when the floating fiber moves at the front roller, that means this is becoming. So, it will be alpha equal to a d minus v 1 by v 1. So, it will be a d minus 1. So, alpha is maximum is there. So, alpha has got range from 0 to a multiplied by d minus 1. So, that is the it varies. So, alpha represents the irregularity generated due to the drafting as a consequence of uncertain movement of the shorter fibers in the drafting zone. So, during the actual drafting, the short fiber movement is uncertain. This is not, we cannot control this movement of the short fibers. So, this deviation, when the floating fiber is, that we have already discussed here. Now, it can be minimized by adopting the different measures to compel the short fibers to move at the back roller speed. So, we want, if we want to minimize this, so we have to compel the fibers the floating fibers to move at the back roller speed till they reach the front roller nib. So, how to do it? So, in the draw frame it is not possible, and draw frame to some extent it is controlled, because in the draw frame the advantage is that we have certain draft, and this is back roller and it is front roller. Now, in back roller the large number of fibers are there than the front roller. So, here the floating fibers will be pulled back by the back roller due to the large number of fibers under the control of the back roller. So, the movement will be towards the close to the back roller speed. So, this becomes towards the lower variation. So, in the draw frame we can manage in this fashion, but when the number of fibers are less, like in roving frame and ring frame, we want this short fiber, floating fibers to move at the back roller speed till it reaches the front roller nib. So, this is done by this is a back roller. So, we do not apply that much draft. So, it is only some brake draft is attached. So, there is no addition that much, but in the main draft front roller and mid roller. So, in between this, so what we do, we use the apron to control the floating fibers. And here in the apron zone, the advantage is there, the apron moves at the speed of the middle roller, that means in the front zone the back roller movement. So, till the fibers reaches at this front roller nip, that means the floating fibers moves at the speed of the middle roller. So, that helps to minimize the alpha. So, because at a back roller speed it is to the floating fiber has to move. So, that way it controls the irregularity. So, that is how we control the irregularity at the by apron drafting system. Okay. So, this moves at the back roller speed till it is reaching. So, fibers movement is controlled here. So, let us consider two zone drafting system and roller setting is equal to the fiber length. So, we are now considering one situation here. Now, from Vesilef's model, y 1 bar equal to d y bar plus the deviation, and for the back zone shear after drafting. So, this is the back zone, shear after drafting will be y 1 bar d 1 y 0 and alpha dash 1, this is at the back zone, and d 1 is the draft at the back zone, there is a break draft which is very low, y 0 bar, y bar 0 is the shear before the drafting, x alpha 1 bar is the average deviation from the normal shear at the back zone. Similarly, in front zone y 2 bar equal to d 2 draft at the front zone which is higher in quantity, and y 1 bar plus alpha 2 bar. Substituting the from the above equation we get. So, this is the, so this we if we substitute y bar in the above equation, what we get, y 2 bar equal to d 2 into y 1 d 2 into this is the y 1 bar plus alpha 2 dash. So, d 2 d 1 d 2, what is d 2 or d 1 d 2? So, d 1 d 2 d 1 d 2 if we multiply it will be total draft in this system. So, total draft is multiplied by y 0 bar plus d 2 is the front zone draft into deviation at the back zone and deviation here. So, ultimately what we get, the total deviation of normal shear is, this is the total deviation. For normal shear it should have been d multiplied by y 0 y bar 0, but it is the total deviation here, and now this deviation has to be reduced. If we can achieve this lower deviation, then we will achieve the we can reduce the drafting wave, okay, or drafting or we can reduce the irregularity, where in the front zone draft d 2 and shear is y 2 and alpha 2 is the average deviation from the normal shear at the front zone draft. So, alpha 1 dash and alpha 2 dash are the average values, and they should be proportional to the range. Okay. The maximum value here is alpha max A d minus 1 that we have discussed. So, alpha equal to k alpha dash k A d minus 1. So, that is the it is the average one at the alpha 1 at the back zone, and at the front zone alpha dash k A d 2 minus 1. Now, what happened if we can set the draft at certain point close to 1. So, in that case the deviation will be more. So, for draft 1 though there is no deviation. So, if the total deviation from the normal shear is set to 0, then the possibility of irregularity will be theoretically minimum. So, that total deviation we want to have 0. So, total deviation from the normal shear is this one. Okay. So, d 2 alpha dash 1 and plus alpha dash 2. So, if we can achieve this one 0, then the theoretically there will be minimum irregularity. So, a solution is possible only, so as they are added. So, this is only possible where either this is 0 or in both the cases the one of this deviation is negative. So, that is either both the things are 0, which is not possible, or one of this parameter is negative and equal, then only it will be 0. Okay. So, any deviation calculated based on the above method using the fiber end shear cannot be negative. So, that we cannot any deviation cannot be negative. So, Grishin showed that a lengthy method to calculate the deviation based on the central point of adjoining fibers. So, there is a deviation. So, and where the deviation can be negative also. So, let us assume that alpha dash 2 is negative. So, here if it is negative alpha dash 2, this is the front roller nib, and in the front roller nib this is the here it is a negative. So, d 2 and here this is the negative value is there. So, alpha dash 1 we have this value, and alpha dash 2 this we have already derived here, this is equal to 0. So, K A, rearranging this equation we are getting this K A multiplied d 1 d 2 is a d minus d 2 minus d 2 plus 1. So, total draft is d 1 d 2. So, we replace it. So, d minus this cannot be constant 0. So, d minus 2 d 2 plus 1 equal to 0. So, where d 2 is d plus 1 by 2. So, that means, so we set draft in this fashion to get minimum irregularity. So, d 1 is, so d 2 is there, d 1 we can set in this fashion. So, we set the draft in this way. So, if we see that if we have say total draft say 10, so the front zone draft will be say 10 plus say 10 plus 1, say if it is say 9, total draft is say, if it is say total draft we are trying to use say 9 total draft. So, total draft is 9. Okay. Now, what will back zone, so front zone draft will be 9 plus 1 by 2, that will be 5, and the front zone this is the front zone draft, and back zone draft will be 9 by 5. So, that in that way we can get the draft distribution. So, we can, using this theory, we can at least try to achieve the minimum irregularity. Okay. So, we will stop here and we will start the next session with the nipping of sliver by rollers. So, in the next session, till then, thank you.